Hello and welcome to a digital lecture for Calculus 2 at Salt Lake Community College. In this video we're going to be talking about section 7.3, Trigonometric Substitution. We basically up to this point we're dealing with situations that you can solve with integration by parts, which we're going to cover in just a second as a reminder. And we talked about how to deal with trigonometric integrals that involve trig integrals or trig functions. What we are going to have here are instances that don't necessarily have trig integrals to start with, but what we're going to do are introduce trig integrals. Overall, what that will do is make it so it's a situation that becomes solvable. Most of these will involve situations where you have a square root sitting around, and those can be very difficult to solve depending on what's inside of that square root. So that's what we're going to be looking for, ones that would otherwise not have been solvable up to this point really with by parts. Or if they are, they would take way too long. With trigonometric substitution, sometimes introducing a trig integral or trig function will make it a lot easier to deal with the integral. A couple things that you're going to need to keep in mind though is that different square roots or different equations and expressions will require different trig functions. We're primarily going to use sine, secant, and tangent, although you could use other functions if you so pleased. And also what we're going to typically do is draw a picture to help us with it. Now, before we go into how to do the trig substitution, what I want to do is do an example of one where we could do it with by parts, and then show how you could also do it with trigonometric substitution. To again show that trig and calculus doesn't need to be done in just one way. Sometimes you can have multiple methods of doing something. We have the integral of square root of 1 minus x squared dx. First, I'm going to show how you would do this with by parts. Unfortunately, we only have a singular term here, so the amount of stuff we could do with integration by parts is limited. We would simply have to take the only thing we have there as u, so 1 minus x squared, and then dv would be set as just dx. Now, finding v is relatively simple, it's just x. Du, however, takes a little bit more work. Du for this is going to be 1/2 times, if I take the derivative of this, I would get 1 over the square root. So the square root would move to the bottom, 1 minus x squared. And then I would also have, by the chain rule, the derivative of the inside, which would be negative 2x dx. So the 2 and the 2 would cancel, so I have negative x over square root of 1 minus x squared dx. That's going to be my du. A little bit complex. So what I'm going to do is now split this up as u times v, so x times square root of 1 minus x squared, minus the integral. Well, that minus will actually make this a plus the integral. Actually, I'll keep this minus for now, and there's a reason for that. Minus the integral of du times v, so I'll have negative x squared, because the x will multiply the x on top, over the square root of 1 minus x squared dx. Now this is kind of hard to solve initially. However, what we can do is try to make it look like what I see in the bottom. On the bottom I see 1 minus x squared, and on the top I see a minus x squared. So all I really need to do is add a 1 to that, and it looks exactly like the bottom. But if I do that, I need to subtract a 1 on top as well to compensate. Now what I can do is split this up. 1 minus x squared minus, and that's why I kept the minus on the outside there. 1 minus x squared over square root of 1 minus x squared minus 1 over square root of 1 minus x squared dx. So I split this fraction up into 2. Reason I do that is because now I can say that I have x square root of 1 minus x squared minus, if I see this as 1 minus x squared to the 1 power and the bottom as 1 minus x squared to the 1/2 power, I simply subtract those powers, and I get, on the top, I get a 1/2 overall. So I get minus the square root of 1 minus x squared. And I can separate that as its own integral. Minus, well, this actually would be a plus, because this minus would distribute, plus 1 over the square root of 1 minus x squared dx. All right, well, this I can actually solve. This is actually arc sine, so that's not too bad. But this other integral is what I started with, and I couldn't solve that before. But like when we had earlier on 7.1 at the end, where we had e to the x times sine x, we can add this to the other side and have 2 times the integral of 1 minus x squared dx. So I'm basically taking this and adding it to there, because I see those as the same thing, equals x square root of 1 minus x squared plus this integral, which actually is arc sine of x plus c. Divide the 2 over, and I get my solution for the square root of 1 minus x squared dx as 1/2 x square root of 1 minus x squared plus 1/2 arc sine of x plus c divided by 2 is still a constant. So that's what I get. Note that that was kind of complex. Some of you may have followed along really well with that. Some of you may have gotten a little lost somewhere. But the thing that you need to pay attention to is that we noticed that we got this integral we started with on the other side, so we just needed to add it to the initial left side there. It's a little complex. If we do this with trig substitution, though, it gets a little bit easier. The way that I'm going to deal this with trig substitution is that I'm going to replace the variable that we have with a trig function. What I notice here is that I have 1 minus x squared. If I think about the trig identities, there are some functions that or identities that if I move around, I get 1 minus x squared. Namely, sine squared x plus cosine squared x equals 1. If I subtract either of these over, I get something that looks like 1 minus something squared. In this case, let's move sine squared of x over. So we have cosine squared x equals 1 minus sine squared x. That means what I'm going to do, maybe if I use a different variable here, let's do theta, because that's the typical variable for trig functions. If I use theta instead, I'm going to call x, I'm going to call it sine of theta. And that means if I call x something, I need to replace it just like if I were to do du. I'm going to call dx, derivative of sine, is cosine. Cosine theta d theta. So then I'm going to say that the integral of the square root of 1 minus x squared dx, I'm going to call this instead the integral of the square root of 1 minus x squared, where x is now sine, so 1 minus sine squared of theta, and dx is now cosine theta d theta. Now, this is going to be important later, but what I'm also going to do is draw a little picture of what I've done technically. If I said that x equals sine x, and I know that sine is opposite over hypotenuse, that means x over 1 defines opposite and hypotenuse. So as a picture, if I think about this as a triangle where this is theta, sine of theta would be opposite over hypotenuse, so x over 1. And then if I solve for the adjacent side, that's going to look like 1 squared minus x squared. So 1 squared is 1 minus x squared. Notice that's what the initial function looked like. Again, this will be important later. Well, now what I have, 1 minus sine squared, we showed earlier that 1 minus sine squared is cosine squared times cosine theta d theta. And square root of cosine squared is sine of theta. Cosine theta d theta. Or sorry, not sine of theta, just another cosine. So then, cosine times cosine gives me cosine squared theta d theta, which we can solve using a half angle identity, which we talked about in section 7.2. Cosine squared theta, I can replace that as 1/2 integral of 1 plus cosine of 2 theta d theta, which is solvable as 1/2 times theta plus, that's going to give me another 1/2 sine of 2 theta plus c. Okay, now how we get all that, or how we get that solution that we just got earlier. Notice that 1/2 sitting outside there. That is actually going to be pretty helpful for us, that we already have this. Sine of 2 theta, that's actually a double angle identity, which we can actually manipulate. We can call this 1/2 theta plus sine of 2 theta is 2 sine theta cosine theta. That's the double angle identity for sine of 2 theta. So the 2 and the 1/2 will cancel to make this just sine of theta cosine of theta plus c. And now we just manipulate and simplify based on that triangle. So 1/2. Notice that we defined x over 1 as sine of theta. So if we said that x equals sine of theta, that means if I take the inverse of sine of both sides, that means inversely sine inverse of x equals theta, otherwise known as arcsine of x equals theta. Which means that theta is just arcsine of x. Sine of theta and cosine of theta I can get from this triangle. Sine of theta is opposite over hypotenuse, so x over 1, so that's just x, so plus x. Cosine of theta is adjacent over hypotenuse, so square root of 1 minus x over 1. So we get square root of 1 minus x squared plus c. And we got now the exact same solution that we did before. I just didn't multiply the 1/2 out. But that's the exact same solution. Solved in a different way. We still even got all the original things of arcsine and x and square root of 1 minus x squared. This method tends to be a little bit not just simpler, because in this case we actually had multiple methods, but there are some other instances that would not simply be solvable at all given what we had before. Or they would take way too much time. In this case, we needed to either employ a very tricky method to use integration by parts in terms of adding the integral over, but with trig substitution, all we need to keep in mind is a triangle that we create with whatever trig substitution we work with. All right, now there's going to be 3 quote-unquote forms here. It just depends on the expressions you have. You'll either have an expression of a squared minus x squared, which is what we just dealt with. We just did 1 minus x squared. And our substitution was a sine theta. In this case, a was 1, hence 1 squared. So just the sine of theta. That means the differential was a cosine. And the identity we were using was 1 minus sine squared equals cosine squared. If we have x squared minus a squared, so the inverse of that, we can't really do sine and cosine too well. What we more accurately would do is just a secant theta, where the differential is a secant tangent, and that's because secant squared minus 1 equals tangent squared. And lastly, if we have a squared plus x squared, we could just use a tangent, where the differential is a secant squared, and then we have the identity as 1 plus tangent squared. Notice that means that we're using 2 identities. We're using 1 minus sine squared equals cosine squared, and we're using 1 plus tangent squared equals secant squared, or the other form of it. So we're only using 2 identities. Now the same table is also given to you on page 486 of your textbook. However, it doesn't give you the differential. It just assumes that you should know how to do those. But I wanted to give those, hopefully that this can help. Now for all these cases, as I note as well on the bottom here, it will be important and it will be imperative to draw the triangle created by this substitution. So it will be imperative to draw the triangle created by the substitution. Always do this. If you notice at the end of that situation we had sine and cosine, I needed to determine what those meant back in terms of x form. And the best way to do that is to draw a triangle. Thankfully, you don't need to be too detailed with this. Don't need to worry really about the quadrant. Just draw a normal triangle as you would in quadrant 1 or something. Just normal right triangle, and determine what opposite, hypotenuse, and adjacent are. That's all you need to work with. Let's do a couple examples of this. Integral of the square root of x squared plus 1 over x. Okay. Now, what we notice here at the top, we have square root of x squared plus 1. That's what we focus on. That's going to be our key that identifies that this is going to be a trig substitution integral. This is of the form x squared plus a squared, where just x is normal and a is 1. So that means that we're going to follow the third form from the previous page. We're going to say that x equals a times tangent, or just tangent of theta. Therefore, we're simply going to call dx secant squared of x dx, which I believe I have up there. Just make sure. Yeah, secant squared. Secant squared x dx. So that's what I'm going to substitute into this. When I draw this, or when I consider that, I say tangent of theta is x, or x over 1. That means if I have my angle measure here, tangent is opposite over adjacent, so x and 1. And then the hypotenuse would be the square root of each of those squared, or x squared plus 1. Whichever side you don't have should be that original term here, whatever square root we're trying to work with. So that can help. All right, so if I substitute it in appropriately, we get the integral of the square root of x becomes tangent squared theta plus 1 over x is now also going to become tangent of theta, and dx is now more complicated than it was before. It is now secant squared x dx, or secant squared of theta d theta, sorry. Again, I did up there, secant theta d theta d theta. Sorry about that. All right. Now that square root of tangent squared plus 1, that will give me the square root of secant squared theta. And I'll put that secant squared theta we had on the outside up top as well. And so overall, we get square root of secant squared is just secant times another secant, should give me secant cubed. Or what I can do, as I would solve this before with some amount of secants, I can do a Pythagorean identity. And what I'm going to do, that square root of secant becomes secant theta. And secant squared, I'm going to replace that with 1 plus tangent squared of theta all over tangent of theta d theta. The reason I do that is because now I can combine those tangents pretty well. This is going to give me a couple integrals. Secant times 1 over tangent. So secant theta over tangent theta. Plus secant times tangent squared over tangent will give me secant times tangent. So I'll say this is its own integral plus secant theta tangent theta d theta. Okay. Now the first one, secant over tangent, that may be kind of complicated to work with because it's not just a u-du situation. However, what you can consider this is, secant is 1 over cosine. Tangent, or 1 over tangent, is cotangent, which is going to be cosine theta over sine theta d theta. And that's going to cancel out those cosines. Integral of secant theta d theta, though, that's solvable. That will just give us secant of theta. Derivative of secant is secant tangent plus c. And so now what I have is the integral of cosecant of theta, or 1 over sine d theta, plus the other two pieces we already solved for. So plus secant theta plus c. And now the integral of cosecant theta, that will give us the natural log of cosecant x minus cotangent of x. That one you may need to look up. plus secant of theta d plus c. Also, these x's should be thetas. Sorry. There we go. All right. Now we have no integrals anymore, but what we do need to do is we need to go back to our original triangle and consider what each of these pieces mean. So, natural log. Cosecant, instead of sine, which is opposite over hypotenuse, is hypotenuse over opposite. So we have hypotenuse, which is the square root of x squared plus 1, over the opposite, which is x. So square root of x squared plus 1 all over x. And then we have minus cotangent. Cotangent would be adjacent over opposite. So minus 1 over x. Oh, that's in the natural log. Plus secant of theta, which is going to be hypotenuse over adjacent. So that's the square root of x squared plus 1 all over 1, so just by itself. And then our plus c term. And that would be our solution. You can combine the terms in the middle if you want to as square root of x squared plus 1 minus 1 over x. That's fine. But this should do it. Okay, and that should cover it. Now, I will say again, if you notice as we were going through the trig, I did some Pythagorean identity. If you find another way of solving through and getting the integrals to simplify and go away without dealing with the integral of cosecant, that should work fine. Even if your answer looks a little bit different, it should evaluate to be the same, just plus or minus constants. Let's do another example, this one with some bounds. So we have from 2 root 2 up to 4, we have the integral of 1 over y cubed times the square root of y squared minus 4. That inside the square root is what we focus on, y squared minus 4. So that means that this is going to look like the second situation, where we have some variable squared minus a squared. So we have square root of y squared, in this case our variable, minus a squared, so that means a is going to be 2 here. Therefore, we're going to set y as 2 times secant of theta, and we set dy as 2 secant theta times tangent of theta d theta. Now the reason that that 2 needs to be there is because when we put that back in, we need to get rid of that minus 4, make it a minus 1. That way it works well with the identity. So what we have here, we have the integral now of, I'll actually use the bounds in a bit, so I'll just say a to b. So I'll deal with the bounds later. Actually, we can deal with the bounds now. Yeah, let's deal with the bounds now because we don't need to simplify later if we already have the bounds. If I say 2 root 2 is my y value, I should be able to find it in terms of theta. So I'll say 2 root 2 equals 2 secant of theta. So divide by 2, we get 2 root 2 equals secant of theta. Or in more normal terms, we get 1 over root 2 equals cosine of theta, otherwise known as root 2 over 2 equals cosine of theta. Now that happens, if we take the inverse of cosine, that happens when theta equals 45 degrees, or as I will say, pi fourths. If we do the same thing with 4, we have 4 equals 2 secant theta. Divide by 2, we get 2 equals secant of theta. Take the inverse, we get 1/2 equals 1 over secant is cosine. And 1/2 equals cosine, that happens when theta equals 60 degrees, otherwise known as pi thirds. So we have pi fourths up to pi thirds. Those are going to be my bounds. Now you may have noticed before that there was a table for this, for when you're putting values into this for a sine, a secant, and a tangent. These are basically the quadrants that you're allowed to use, and this is basically what would happen when we would do inverses. If you're doing for sine, you have negative pi halves to pi halves, so that's quadrant 4 and 1. A secant, you have quadrant 4 and 1, and a tangent, you have 0 to pi halves, so that's just quadrant 1. So that kind of tells you what kind of angles you could work with, because theoretically, when we have root 2 over 2 equals cosine, that could happen either in quadrant 1 or quadrant 2. Since we are limiting to quadrant 4 or 1, it has to be quadrant 1. So we have root or pi over 4 to pi thirds, and that's what I'm going to do to replace each of my integrals now. I'm going to erase that so I have room. So I'll say integral of pi fourths to pi thirds, and now when I'm done, I shouldn't need to simplify back in or plug the values back in. All right, dy is going to be my 2 secant tangent, so that's going to go on top. 2 secant theta tangent theta. It's going to end up on top. Y cubed, where y is 2 secant, will give me 2 cubed is 8 secant cubed theta times the square root of 2 secant squared or 2 secant theta times itself will give me 4 secant squared theta minus 4. Again, that 4 coming from 2 squared and that 8 coming from 2 cubed d theta. All right, so this expanded and looks even uglier, but again, this will start to reduce down relatively quickly. All right, immediately we see some things that we can cancel. Particularly, I see a lot of these constants, and I'm going to deal with those first. I see that 4 and that 4, and since that's in the square root, I can simplify that as the square root of 4 times secant squared theta minus 1. So I can pull the 4 out and make it a 2. That will give me another 2 on the bottom. So I'll have overall 2 times 8 gives me 16, and a 2 on the top. So I just pulled all the constants out. Pi fourths, pi thirds. So we'll have secant theta, tangent theta on top. On the bottom, I still have the secant cubed theta, and I have the square root now of secant squared theta minus 1 d theta. So I just pulled all the constants out at once. That 2/16 can also become 1/8. So now 1/8, pi fourths, pi thirds. I have secant tangent on top. Going to keep all things together until I simplify everything. Secant squared theta minus 1. This gives me tangent squared theta. And then when I do the square root, I just get tangent. So secant cubed theta, tangent theta, d theta. That allows me to eliminate tangent and tangent. A secant with one of those secants up in the power, so instead of having 3 in the bottom, I'll have 2. So now I have 1/8 integral of pi fourths to pi thirds of 1 over secant squared theta d theta, otherwise known as 1/8 integral of pi fourths to pi thirds of cosine squared theta, because that's the reciprocal of secant squared. Cosine squared, what we can do is do a half angle identity with that, which is going to pull another 1/2 outside to make this 1/16. I'm multiplying that by 1/2 because of the half angle identity. And we get 1 plus cosine of 2 theta d theta. Now I can solve that integral, and we get 1/16 times 1, which just becomes theta, plus this becomes 1/2 sine of 2 theta, and we don't have a plus c because in this case we have bounds from pi fourths to pi thirds. Now, if we were doing one of the previous ones that didn't have bounds, we would then need to draw the triangle and figure out what each of these would represent. But we have bounds, so we don't need to do that. We could just plug in the bounds appropriately. So I'll keep the 1/16 outside here first. Let's plug in pi thirds. Pi thirds into theta just gives me pi thirds. Plus 1/2 times sine of 2 times pi thirds, which is sine of 2 pi thirds. And sine of 2 pi thirds will give me root 3 over 2. So that's a little bit of a unit circle. Plug in pi fourths, we get pi fourths where theta is, plus 1/2 times sine of 2 pi fourths, which is sine of pi halves, and sine of pi halves is 1. So, put this together. Let's see, we have pi thirds minus pi fourths. I'll deal with that in a bit. 1/2 times root 3 over 2. So I have root 3 over 4. And 1/2 times 1 will give me another 1/2. See if we can put all this together. I see common denominators of 3 and 4, so the lowest one would be 12. So I have 4 pi over 12 minus 3 pi over 12 plus 3 root 3 over 12 minus 6 over 12. So 4 pi minus 3 pi gives me just pi. And then I have plus 3 root 3 minus 6 all over 12 times 16. 12 times 12 is 144. Another 4 times 12 gives me 48. So if I put all that together, I get 196. All right, and that's that. Not the prettiest looking one. You might be able to simplify it another way if you want to, but that's probably fine. Good enough. All right. Moving on to a couple more examples. We have example 4 and 5 here. This first one, again, we have bounds, and we are focusing on the fact that we have another square root on the bottom. That's our big key that we're going to be using trig substitution. So since we have the square root of something squared minus x squared, that's going to be our first situation, which we dealt with as the example 1. So what we're actually going to use is sine here. Since this is the square root of 6 squared minus x squared, we're going to say that a is 6. So therefore, x is going to be 6 sine of theta, and dx is going to be 6 cosine of theta d theta. Okay. Furthermore, we have bounds, so let's figure those out. We first have 3 on top, so I'll say 3 equals 6 sine of theta. So if I divide 6 over, I get 1/2 equals sine of theta. Sine of theta is going to be defined in quadrant 4 and 1. Since this is positive, we're talking about quadrant 1. And this specifically happens, 1/2 happens when sine is at pi over 6. Again, this might require some unit circle stuff. If you plug in 0, you get 0 equals 6 sine of theta. So you get 0 equals sine of theta. And that happens, again, between quadrant 4 and 1. That happens when theta equals 0, or 0 pi over 2. We could say 2 pi, but that would be outside the bounds. We don't want it to rotate too much. So just 0. So we can replace this whole thing. We can say, instead of 0, 3, 0 to pi 6. On top we have x, which now becomes 6 sine of theta. And dx is also going to introduce another 6 cosine of theta to the mix. And on the bottom we have the square root of 36 minus 6 sine theta squared, which is going to be 36 sine squared theta. All right. So let's see here. 0 to pi 6. On top we have 6 times 6, which is going to give me 36. I'll pull that out. On the bottom, this is going to become the square root of 36, 1 minus sine squared theta. And I can pull that 36 out to make it 6 come out of the square root, so we get 6 on the bottom. So then we have sine theta cosine theta all over the square root of 1 minus sine squared theta. d theta. Solving for that, 36 over 6 gives me 6. From 0 to pi over 6. On top we have sine and cosine. On the bottom, 1 minus sine squared becomes cosine squared. And the square root of that is just cosine, which is going to eliminate with cosine on top. So we just have the integral of sine of theta d theta. Look how easy that solution became. It was very, very complicated, and it simply became a single trig function, which we could do any day of the week. This is going to become negative 6 cosine of theta. Integral of sine is negative cosine. From 0 to pi over 6. And since we took this time to find the new bounds, we don't need to plug in anything new. So we just need to plug in those bounds directly. We get negative 6 I'll keep out for a moment. Pi 6 into cosine, that's going to give me root 3 over 2. Minus 0 into cosine is not 0, it is 1. So we get overall negative 6 times root 3 over 2 will give me negative 3 times root 3, so negative 3 root 3. And negative 6 times negative 1 gives me positive 6. So 6 minus 3 root 3. Nice and simple. That's how a lot of these will go. Initially, we could not really have done that too nicely. We could have done a UDU situation, but this, just doing u of 36 minus x squared, but this also works very, very nicely. Lastly, look how gross this one looks. We have the integral of x squared over 3 plus 4x minus 4x squared to the 3 halves. This is going to scare some people. Okay, first because of how this looks. But let's rewrite this. Let's try to get this of this form. I see that 3 halves there. That gives me the implication that maybe we'll use trig substitution, but I want to make this look like a square root. 3 halves, or an exponent to the 3 halves, is the same thing as taking something to the 1 half and taking that to the 3rd power. So what I'm going to do is rewrite this as the square root of 3 plus 4x minus 4x squared to the 3rd power. That's what I'm going to consider this as. Now that this is in the form of a square root, what I'm going to try to deal with is this complicated term on the inside. In order to do that, I'm going to apply the process of completing a square, which is going to be a little bit complex in this case. First, I'm going to take the pieces with the variable, and I'm going to put those together. And what I'm also going to do is pull out a negative out of them. So I see negative 4x squared. I'll pull the negative out to make it negative quantity 4x squared. Negative out of the positive 4x will make it a minus 4x plus 3. All right. Now, in order to complete the square, i.e. to make it of the form of ax plus d sometimes squared, what I really need to do is find what d is. The quick way to do d is going to be b over 2a, where in this case b is the coefficient on the single x term, and a is going to be the coefficient on the x squared term. So b is going to be negative 4, and 2a is going to be 2 times 4. So that's going to be 4 over 4. This is going to be negative 1/2. So we get the integral of x squared over dx, or over the dx on the outside, minus, we get, if we pull a out, which a is 4, we get minus 4 times x minus 1/2 squared plus 3. However, if we contributed to this, what we did is really we added a new system. Specifically, what we did is we added some amount of constant as determined by this. What we specifically did is if we square negative 1/2, because that's what would happen if we were to FOIL this back out, negative 1/2 squared will give us a positive 1/4. And if we multiply that by negative 4, what we actually introduced was a minus 1 to the overall system. Since we introduce a minus 1, we need to compensate by adding a plus 1 outside of the square. So that would be completing the overall square. Now, with that done, again, there's a couple different ways of completing the square. It depends on how you like to do it. What we see here is 3 and 1 make 4, and we also have that 4 here, so what we can actually do is pull a 2 out of the square root. And what we have left is 3 plus 1 was 4, took that 2 out, so we just have a positive 1 minus x minus 1/2 quantity squared. So nice and easy. All right, now that we have this as technically a squared minus y squared, you can consider this. This is like, again, the first form, so what we're going to do is replace that x minus 1/2. We're going to replace that with sine of theta. If we add that 1/2 to the other side, we can also find that dx is going to be cosine of theta d theta. What I do also need to keep in mind, because I actually dropped it here, is that there was this exponent of 3. So this should be to the third, and likewise this is to the third. So that means when I pulled that 2 out, that's actually 2 to the third as well. And now we can replace things appropriately. And so that 2 to the third is 1/8 on the outside. X is going to become sine of theta plus 1/2 squared. Dx is going to introduce another cosine of theta on top. And on the bottom, we have the square root of 1 minus this expression becomes sine squared theta. And this is also cubed. Overall, I'll deal with the top in a moment. Sine of theta plus 1/2 squared cosine theta d theta, which I did not have in the last one. On the bottom, 1 minus sine squared becomes cosine squared. Applied to the square root just becomes cosine, but then to the third becomes cosine to the third theta. So let's see what we can do with that. Okay, so this is going to take a little bit of manipulation. Again, we're not done really yet. On top, we see that we have a complicated term that also has a constant. Let's make that constant a little bit simpler. Let's pull a 1/2 out of those pieces. Again, I'm doing this my own way. If I pull 1/2 out of sine, I get 2 sine of theta plus 1 squared. One of the cosines is going to cancel, so I'll just have cosine squared on the bottom. D theta. And now I can have that 1/2 squared is going to make that 1/4 times 1/8 will overall give me 1/32. Times the integral of now I have this sine term. Notice that this is all squared. So 2 sine theta plus 1 squared and cosine squared on the bottom as well. So now this is an overall 2 sine theta plus 1 over cosine of theta. All of that is squared, so I can put it all together. And hopefully now I can make that into a simpler term by combining. So 1/32 integral. Again, these are not always going to be the shortest problems. 2 sine over cosine. Sine over cosine is tangent, so that's just going to be 2 tangent theta. 1 over cosine, that's secant of theta squared, d theta. Probably other ways of approaching that, but that's probably the fastest way that I saw, making it so I don't have fractions anymore. The only fractions are sitting on the outside. And now if I square that, I get 2 tangent theta times itself will give me 4 tangent squared theta. Plus, I'm going to get 2 tangent theta times secant twice, so I'm going to get 4 tan theta secant theta. Plus secant squared theta d theta. All right. Most of these are solvable as they are. Secant squared theta, that's solvable. Tan theta, secant theta, that's solvable. Both of those are able to be applied. But tangent squared theta is not. We do need to replace that with secant squared theta minus 1 with its Pythagorean identity. Plus secant squared theta d theta. So we get 1 over 32. 4 times secant squared plus another secant squared gives me 5 secant squared theta. Plus 4 tan theta secant theta. Minus 4 d theta. I'm going to rewrite that down here. This got more squish than I thought. I thought I had more room. So 1 over 32. 4 times secant squared plus another secant squared gives me 5 secant squared theta. 4 minus 1 will give me minus 4. Plus 4. I'll make this more familiar looking. Secant theta, tangent theta. D theta. All right. Now all these are solvable. All right. The integral of secant squared is tangent, so that's going to be 5 tangent of theta. The integral of minus 4 is minus 4 theta. And the integral of secant tangent is secant. So that's 4 secant of theta plus c. Doesn't matter what that is. Now this is going to take a little bit because we do need to consider the triangle that we had introduced. We said that originally, sine of theta was x minus 1/2, according to what we had originally up here. Yeah, we said sine of theta was x minus 1/2. So that's how we're going to define our pieces. X minus 1/2 over 1. So x minus 1/2 is going to be my opposite over my hypotenuse. And my adjacent side is going to be the square root of 1 minus x minus 1/2 quantity squared. All right, so then we can define all of our trig functions. None of these are overly complicated. Tangent is going to be opposite over adjacent. So that's going to be x minus 1/2 over the square root of 1 minus x minus 1/2 squared. Minus 4 times theta, where theta was sine of theta equals that, of x minus 1/2. Because we defined that sine of theta was equal to x minus 1/2, so taking the inverse gets us the opposite. Plus 4 times secant, which is adjacent over hypotenuse, or hypotenuse over adjacent rather. So that's 1 over that square root. So 4 times 1 over square root of 1 minus x minus 1/2 squared, and then that parentheses. Okay. Now at this point, there's probably some simplification that possibly could be done. For example, I do see we have common denominators here. So we should be able to add this at least a little bit, maybe make it a little bit nicer looking. So 1 over 32, this is 5x. So 5x minus 5 halves plus 4. So minus 5 halves plus 4, 4 is 8 halves. So that's plus 3 halves over the square root of 1 minus x minus 1/2 squared. minus 4 arcsine of x minus 1/2. So I guess that's probably as simple as you could get, and that would be our simplest solution. So yeah, not the easiest thing to get back, but we were able to get back to c. Oh, okay. So by the way, there should be a plus c out here. Yes. So there should be plus c's on all these. So not the easiest thing to get. It takes a little bit of time, obviously, but that's kind of how calc problems tend to go. And we didn't really start off with something that was very easy to solve, so it did need to take some maneuvering. And this really wasn't solvable in any other way, at least in any of the ways that we've introduced up to this point. So hopefully that gives you an idea of a lot of the simpler ones, like the fourth example, which took almost no time, and what the complicated ones can look like this fifth example that takes a lot more time. A lot of things to keep in mind. Always draw a picture, particularly if you do not have bounds. If you do not have bounds, then you need to make sure you plug x back in. If you do have bounds, you should be able to find your new bounds, and you don't need to worry about plugging back in. And also keep in mind, like with 7.2, if your solution doesn't look exactly like it does in the back of the book, that doesn't mean that your solution is wrong. It just could look a little bit different based on the values that you got. So it can change up a little bit. For example, this square root, or this first expression that I have, the 5x plus 3/2 over that square root, that can be written in a few different ways as well. So this is not the only solution that you have. With a little bit of algebra, you can move that 2 to the bottom, put it into the square root, and make this simpler, and make it even look like the original square root that we had, but it's not exactly necessary. With that said, that's everything that I have for section 7.3. If you have any questions, feel free to put them in the comments below or ask your instructor directly. I hope that you have a nice day.